Well, now we are going to begin the investigation of curve sketching, that is, graphing functions without a calculator, without a graphing calculator. And really what it boils down to is being able to gather the information that we've done in the last few sections, that is, determine where a function increases and decreases, determine where a function has a relative maximum and a minimum, determine where a function is concave up and where it's concave down and where inflection points are, and then a few other pieces of information like where it crosses the y-axis, a y-intercept, or if easily available, where it crosses the x-axis or the x-intercepts, and what we know from previous courses, like things about vertical asymptotes or horizontal asymptotes when we're talking about rational functions. And the process is one really of applying that information and gathering the information and organizing it in a way that helps us visualize what's happening. So that's what we're doing here, is we're going to gather and organize information. Now, I'm using the process of something that I call a sign table. And I've started the sign table below. And I'm just going to fill in the sign table, and as we go, I'll tell you why. But this is the sign table for the particular function that is f of x is equal to x cubed plus 3x squared minus 9x plus 5. Now, I've written the first line of this sign table just to to discuss it and see how we gather information for it before your attention is distracted. So let me just show you that here's what we have. In the very first column, you see we actually have, what, 5 different columns? A column of x values, which is either intervals or specific values of x, a column for f of x, which we fill in only when we have a specific value of x, and then a column for the derivative and the second derivative, first and second derivative. And in those we'll have either pluses or minuses or zeros or undefined. And of course, pluses when we know that the first derivative is positive or negative in a particular interval. And then in the last column are our conclusions, basically, the characteristics of the graph based on the pieces of information we have in that row. So for instance, we see here that the first derivative is positive, and so we know the graph is increasing. And we see the second derivative is negative, so we know that the graph is concave down. So if we know the graph is increasing and concave down, then we understand that the graph has that shape. And that's going to help us understand the big picture of what the graph looks like. Now, in the process of all of this, here's what we've got. I'm not going to go through the details of learning the information, calculating the information. I'm going to show you what a filled out sign table looks like. In this case, the next value that we have is x, is a specific value, -3. And -3 happens to be a place where we have a critical number for the first derivative, and that critical number is from when the first derivative is 0. So actually what we would normally do is we would go through our table and we would fill in, and truthfully what we'd do is first fill in the first column, the intervals and specific values of x. And the intervals and specific values of x are based on the critical numbers of the first and second derivative. So we'll have a bunch of critical numbers, and then from those critical numbers we break the real number line into the appropriate intervals. And so the top of this column happens to be the left side of the real number line, and the bottom of this column will happen to be the right side of the number line. And we actually have, and when we actually do one for real, you'll see we actually have, oh, hold on just a moment. Well, the reason for my break. I've actually been away for a little bit of time here, and you can see that I've added another row, and actually I made it too wide, didn't I? Didn't even notice that till now. And the reason that happened is because I noticed that I didn't have enough rows. So the issue is that we take these critical numbers and we break up the real number line into all the appropriate intervals. And the critical numbers that I actually found out that I have, let me show you below. When I did the calculations, I got a critical number of -3, and I got a critical number of -1, and I got a critical number of +1. Okay, so now those critical numbers, some are critical numbers for the first derivative and some for the second derivative. But overall, I have 3 critical numbers, and so it breaks my interval, my real number line, into pieces. The pieces from -infinity to -3, and then -3 is the breaking place. And then from -3 to the next critical number, which is -1. And then -1 is the value of x where it breaks again. So I have a specific value of x. And then the interval from -1 up to +1. And then, of course, x value of 1 is a critical number, so we might have something special happening there. And then finally, from 1 to infinity. So when we're filling out a sign table, after we find out what these critical numbers are, we know how to fill out that first column. It might take a little practice, but we do. And then we go a little bit further. The next thing we'll do is fill in zeros into the table. And so, for instance, we have, in this problem, I discovered actually for the first derivative, the critical numbers were -3 and +1. So these two numbers are critical numbers for the first derivative, f prime critical numbers. And they were critical numbers where the first derivative was 0. There were no places where it was undefined. So for those two critical numbers, you see, I put a 0 in the column for the first derivative because that's where the first derivative is 0 at those two critical values. And then the other critical number that we have here, -1, that came from finding the critical numbers of the second derivative. There's only one. And that was where the second derivative was actually equal to 0. So at x equal -1, the second derivative is 0, and so I fill in a 0 for that position in this table. Okay. Now, another thing that we'll do is because when we have a critical number of the first derivative, we might have a maximum or a minimum. And of course, that maximum or a minimum is a y value or an f of x value. So it's important when we have a critical number or a specific value of x that we actually calculate the y value that goes with it. And so I use the function f, I put a -3 into the function f, and I got a y value of 32. And then I did the same thing for the x value of -1. And when I put -1 into the function f, I calculated and got a y value of 18. And then likewise for the value here when x is equal to -1, the y value that goes with it happens to be 0. So that's kind of the way this starts. And then the next thing that will happen is we'll do some testing. And we'll decide, for instance, in the interval from -3 to -1, I'm talking about this row. In the interval from -3 to -1, then what we'll do is we'll decide whether the first derivative is positive or negative. In this case, I found out it was negative. And I'll actually just go down this entire column. I found out the first derivative is negative here, found out the first derivative is negative here, and then at the very last of this column, in the interval from 1 to infinity, I found out the first derivative is positive. And then we basically do the same thing for the column for the second derivative. We determine in each of the intervals whether the second derivative is positive or negative. And so I found out that it was negative here. I found that it's negative in the interval from -3 to -1. Of course, at 0, we already had that as a critical number. And then from -1 to 1, I found out the second derivative is positive, and then I found out it was positive, and then I found out it was positive. Of course, this is why it's called a sign table. is for the most part we're putting positive or negative signs in the columns for the first and second derivative. Now we don't care about positive and negative signs for the function f. We only care about the specific y values that go with the critical numbers. Now, we read across each of these rows and determine from what we've filled in what we know about the graph. For instance, in this row where x is equal to negative 3. Well, we could interpret this two ways. So I'm talking about this row, okay? I'm just explaining how this decision is made. If I look above the row, the first derivative is positive, and if I look below, the first derivative is negative. So that means we had a change in sign from increasing to decreasing. Well, that means it went from doing what? In fact, we can fill out the row below. Let's look at the row below. If the first derivative is negative, then the function is decreasing, isn't it? And if the second derivative is negative, then it's concave down. Now, that tells us that we're decreasing and concave down, so we have this shape. And if you think about the first row and this third row, that already tells us that we have a minimum. But the table tells us that because we change from increasing to decreasing by looking at the positive to the negative when we went across 0 for the first derivative. So I'm looking in the first derivative column. And so that told me already that I had a relative maximum. So that's what that told me. In fact, I could have looked at this. I could have looked at the 0 in this column, in this row, in the first derivative. And then I could have said, oh, well, look, the second derivative is negative there. And that means we're concave down. And so if we're concave down and we have a critical number of the first derivative, that means we have a maximum, doesn't it? Regardless, in either case, I could tell that we had a maximum. And I've already got the point listed, see? The maximum has an x value of negative 3 and a y value of 32. That was the usefulness of actually calculating that y value. The maximum is 32, but it happens at that point. And we're going to be graphing this in a moment, so knowing that point's important. Okay, let's skip down now to where it says x is equal to negative 1. And when we look at where x is equal to negative 1, we see that the first derivative is negative, negative, negative on either side, isn't it? And so we don't have a change in sign. And of course, that's not surprising here because negative 1 is a critical number for the second derivative. So we shouldn't have been looking for a relative maximum or minimum there. And when we have a second derivative critical number, what we're looking for is an inflection point. And we see in that second derivative column on top is a negative and below is a positive. So we have an inflection point. We have a change in concavity. And so we know we have an inflection point, and we'll just say that, inflection point. Okay, and in fact, that inflection point has an x value of negative 1 and a y value of 18. And so now we know how to actually place that on the graph. Okay, so we go to the next row, and in the next row, we don't really have anything special going on because there aren't any zeros. But what we do know is that we have a negative first derivative. If we have a negative first derivative, then the graph is decreasing. And we also have a positive second derivative, so that means the graph is concave up. Okay, let's move on. The next to the last row. Well, in this case, we have a first derivative that has a 0 value, so it's a critical number. We're looking for a maximum and minimum. And notice on top we have a first derivative that is negative, and below we have first derivative that is positive, a change in sign. So that means it was decreasing and then it increased, so we actually have a relative minimum, don't we? And we actually could have told that by looking at the plus in the second derivative column. If we have a critical number of the first derivative and the second derivative is positive, then that's when we have a minimum because we're concave up. Okay, anyway, the relative minimum happens at the point where x is 1 and y is 0. That 0 is from the f of x column. And then we look at the very last row, and we see plus for first derivative, plus for second derivative, so that means we're increasing. The graph is increasing, and it's also concave up. Oh, I should have gone up here at this next to this particular row and noticed, oh, it's decreasing in concave up, which means it has this shape, doesn't it? Whoops, it has this shape. And then down below, it's increasing in concave up, so that means it has this shape. So basically, we have this, if you notice all the shapes I have written down this column, if we could put them, the top on the left and the bottom clear to the right, I'm just going to rough this in. This isn't our graph yet, but you see we have this shape, then we have this shape, then we have this shape, and then we have this shape. And so putting all those together gives us an idea of what this graph is going to look like. And in fact, that's what we want to do next. I want to give you a little bit more information, and here's the information that I've calculated about this. I found out that the the y-intercept is 0.5. Okay, so I've done some calculations, and this is not a hard calculation. Found out the y-intercept is the point 0.5. That's an important point to find because it's usually easy for us to find. Now, sometimes the x-intercepts are very difficult for us to find, and that's not really what we're focusing on here. But in this particular graph, I had some information, and I grant you it would be hard for us to know the x-intercepts by looking at that function. So I'm probably not really worried about this for you. But in this case, I found out -5, 0 and 1, 0. So -5, 0 and 1, 0 are two x-intercepts. Let me get at my graphing paper here. We're going to make a small graph using this information to the right in this blank space. But let me get that ready now. Okay, I may have crammed this in a bit, but we'll go ahead and gather this information and get us a nice sketch of this graph. Notice that, of course, I've got two different scales for the x-axis and the y-axis, and that's based on the values I see for f of x. See, I have a y value that's as big as 32, but when I look down the column where my intervals are, I have x's of -3 and x's of -1 and a +1. And so those x's aren't very big, but my y values are. And so I've got to have two different scales here. Of course, down here would be where -10 is, wouldn't it? Now, so let's start out by plotting some specific points. For instance, -3, 32 is a relative maximum. Let's get that on the graph. So we find out where x is -3, and then we go up, 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 up. Just a little bit above 30 would be where 32 is, wouldn't it? So we know that this position is a relative maximum, and so we know the graph is going to look like this right there, don't we? Okay. And then we also know, I'm going to jump down to the relative minimum, and that's at relative minimum is at 1, 0, isn't it? So right here we have a relative minimum. Okay, so that position we have a relative minimum, so we know the graph has to look something like this there. I'm just roughing that in. Now we happen to know also that we've got a y-intercept of 0, 5, and so this is where 0, 5 would be. And we actually happen to have two x-intercepts, -5, 0, so that's here, and 1, 0, and we've actually already got that on there. Yes, that is an x-intercept. It doesn't go through the x-axis. It touches it and turns around. Now, the one point that I don't have plotted here is the inflection point. And remember, that happens at -1, 18. -1, 18. And so we'll say that's roughly here. We'll call that about right here. Now, an inflection point is where it changes concavities. And so in this graph, it's going to be a little bit hard to tell, but it's going to be changing. Let's see, what did it change from? Oh, from concave down to concave up. So sometimes that's hard for us to actually draw in, but it's sometimes a very slight change of cupping down and cupping up, and that's really what we have here. But we have a good idea now what this looks like, that at this relative maximum, it's doing something like this, isn't it? And then it comes on down here, and it has just a slight change now. Now it's supposed to be cupping upward, okay? And then it hits this relative minimum and turns around and starts going up. And so from here that we know it goes up further. Now it's not pointed at those. I've got things squeezed in so much. My exercises are so close together, it makes it look like those are changing rapidly, but actually they change more slowly than I've shown. But there's a good representation of the graph based on the information that we had in the sine table. We may practice another one of these, and then of course the next thing I want to do is actually fill one out. Maybe that's what we ought to do next, fill one out based on the function itself. I want to make a note here before we go on to some more examples. In your homework in my math lab, you're going to be asked to fill in a sine table. You're going to be given a function and create a sine table that will be available to you and fill it in. And it'll give you directions very specifically, but I want to make sure that you are paying attention to those directions, because the computer is not going to recognize you writing increasing or concave down or something of that nature for when we're filling in the sine table. I'm sorry. So remember, I'm just kind of giving you an idea of what this is going to look like. You're going to have this sine table that's going to have many rows. Okay, I'm just looking at one row. It's going to have many rows. It's going to have intervals here, and then it's going to have an f of x and an f prime of x and an f double prime of x, and then it's going to have your conclusions. So, okay, so we're going to put conclusions over here. And of course, we might write something like increasing, okay, or might decide increasing, and then we might decide also concave down. Now, what I'm referring to is that if those are your conclusions, you're not going to type out increasing and concave down. Okay, what you would put, I'm going to put this out here, is to say increasing, you're going to put this little housetop character called a caret. Okay, you're going to put that in, and then a comma, and then concave down, we're going to put what is the intersection symbol. Now these symbols are going to be, remember when you're in my math lab, there's a little tool palette out here. Okay, and in that tool palette is where you're going to find those symbols. So let me give a summary of those real quickly. If you need to if you need to have a conclusion of increasing, then you're going to use the little symbol that's a housetop character. Remember, that will be in the tool palette. For decreasing, you'll use a downward, looks like a downward arrowhead, and that will also be in the tool palette. It looks kind of like a V, doesn't it? When we're talking about concavity, concave up, we will type in the union symbol, or input the union symbol, and that's in the tool palette. And concave down, as I said, will be actually the intersection symbol, and that will be in the tool palette. So that will be this symbol. Now, if we have a relative maximum, and remember these symbols will need to be separated by commas. If you have a relative maximum, then what you will type in is MAX for maximum. And if you have a relative minimum, then you'll need to type in MIN. And if you have an inflection point, then you'll need to type in IP for inflection point, IP. And so anyway, those are the things that you're going to need to enter in the conclusions column so that my math lab will understand and interpret what you're trying to communicate.